Hey guys, welcome back to AlgoYogi. We are doing tree series right now. Our next problem in the list is binary search tree iterator. Let's go to the problem on LeetCode. So the description is quite simple and it's one of those design problem that is asked in the most of the time. It's like the on-site interviews and it's part of those big 3 interviews, and this is one of the problems that's usually asked when they're asking like some design or implementation kind of question. So binary search tree iterator, BST iterator, is the constructor class, and then we have two main methods that we need to implement, and one of them is hasNext, which returns a boolean value if we have any values left after the current pointer. And then we basically have next, which will return an integer value basically, and move the pointer to the right, and then returns the number at the pointer. So yeah, quite easy. So now tell me, if so initially we will be pointing to the root. So there are quite a few ways of solving this problem, and they all have different time complexities, and we will basically implement the best one, but we will talk about the one that have a bit higher time complexity. So I think when it's given to us, the BST, so just tell me, initially we are pointing at the root. Now, what I have to do in order to basically tell if I'm pointing to, let's say, the first value in my in-order traversal. So if I happen to iterate, let's say, this tree, this tree, then it would be 3 first, 7 first, 9, 15, and 20. I think you get how I did the in-order traversal. And initially I will be pointing at 3, right? And then all these functions hasNext and intNext, I could just simply say, and this will be my pointer pt cpt, let's call it cpt, which is current pointer, and that is pointing to the first value, which is the leftmost value in my BST. So this is right here, okay, the leftest value in my BST. Now I could basically keep returning this value as part of next, and when the boolean asks me if I have next, so there are basically values that I actually do, and then they're going to keep calling it, and we just keep shifting our pointer whenever we are being called next. So the pointer will be keep switching this way, this way, this way, and until we reach the last, and then we don't have any more values to return. So that's the whole point. Now this is one way of solving it, and it is basically gonna take big of n time complexity, because we're gonna iterate over everything, and then we're gonna so also store them into our array, and then keep moving that pointer next. However, yeah, space complexity is also, and however, there is a better solution, which is, how about using the space complexity big of h and time complexity big of 1. Unless it's a really unbalanced binary search tree, we can definitely implement a solution that has this particular complexities. Now how are we going to do? Instead of basically storing the entire array into our entire tree into our stack or array, how about I just only go up to the leftmost child, and I just store all of these into my stack. So it would be 3, and then 1, and then 0, and then I'm pointing to 0, and then I'm pointing to 0 as my current basically current value, current pointer, or maybe. And then whenever I'm being asked in my next, then I return this value. However, I basically try to append its left, or try to explore the right side of this node. Now 0 itself does not have anything on its left or right, so we're gonna pop this out. This gets popped out, but when we pop out 1, we can return 1 because that will be our next value, and in order traversal, right? So let me remove this. So in my in order traversal, this will be my next value. However, I will have to take care of the right side, and I do it only when I'm visiting that node. So I will pop out 1, but at the same time I will start exploring this subtree, and it's not just adding this value. I will definitely add this value, but it's about going towards left of it, towards the leftmost child, and then pointing my current pointer over there, and again repeating the same thing. So it would be a case where I have space complexity of big of h and time complexity of big of 1 in the best case. Alright, so let's implement that solution, and I think once I implement it in the code, it will be quite simple to understand. So for the constructor, we are going to have let's say a stack to store the nodes in the path when we are going to the leftmost child. And here basically we don't need to do anything, I guess. It's just we have a stack, and but no, I think initially we have to at least put something in our stack, which is like from the root to its leftmost child. So that would be, we have a while loop. While root could be none, then we would return none. While root stack.append, I think it's going to be self.stack since it's a class. Self.stack and stack.append, and I'm appending the root currently, the node, and then I will point root to root.left. Has next would be return if len self.stack is not equal to 0. If it's not equal to 0, that means we do have some values and they need to be popped out and appended to the stack and keep pointing using the next function. Now for next, now if somebody is asking what's our next value in our array or in order traversal of BST, then it's going to be what we pop out from the stack, because so far we have traversed to the leftmost child, and that is the first node that would be in our in order traversal of binary search tree. So let's pop out the topmost value from our stack. So we can return this rest.value value, but at the same time, as I said in my when I was explaining on the iPad, that this is where we happen to explore the right side of my current value that I'll be returning. So in this case, I'm returning result, but at the same time I want to process whatever values will be in my BST on the right subtree of my current node. So I will just assign current pointer to the right of my rest, and while cur, I will keep appending it to my stack because they are also needed to be processed, the part of the tree, right? So stack.append self.stack.append. I don't want to make that mistake because then I wouldn't be able to run it. We're writing the most efficient solution. We don't want to make mistake. Okay, now that's it. We just append cur, and after that we just cur dot left again. We keep going to the left, and again the same cycle happens, and we will just keep popping it. Right, so that's it. And I think, let me zoom out and see if we are doing everything correct. And it does look correct so far. So let's try to run it on examples. And yes, it passes the example. Let's submit it. All right, let's write the time complexity. We already discussed time complexity would be big of 1. In average case, you can say, or like the best case, or like most of the cases. However, there might be a case where the tree is basically like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's like a linked list. In that case, yes, you would, our space complexity would be big of n, and time complexity would be big of I would say n as well. But here in this case, space complexity is going to be h in best case, and time complexity 1, because in average case we are only using constant amount of time. All right, let's go back to AlgoYogi and mark our problem solved. But do remember, we can definitely solve this problem using just basically initially this stack. You could just create an array. We can create an array and iterate over the entire array using a DFS or BFS whatsoever. Doing the in-order traversal, store all the values, have a current pointer pointing to the first value, and then keep checking if it is greater than in our has next function. Keep checking if it is in our bound, and we do have some values. Then return true, otherwise return false. However, in the next, just keep returning the value at our next pointer and keep moving the pointer to the next value in the array. All right, see you guys in the, I think you can implement that. That's pretty easy to do. See you guys in the next problem. All right, bye-bye. I think we did mark it solved. We did, yes. All right, bye-bye.